So I'm Raphaël, professor at Chalmers in Sweden, and the talk I'd like to give is about microwaves, acoustics, and optics, and molding their flow at the quantum level. And so I'm one of the many people in a center in Sweden called the Raphaël Center for Quantum Technology. So this is a privately funded center in Sweden, which has roughly 150 people now all over Sweden, where the goal is, among others, to build a 100-qubit superconducting quantum computer. Then there's also an excellence program with various more exploratory activities, and I mean the excellence program. And so the lab, which I'm heading, is called the Quantum Photonics Laboratory. And photonics there, I mean both optical and microwave photons. And so what the logo is sort of visualizing here is the microwaves, the optics, and the mechanical waves which are interacting with each other, hopefully at the quantum level. To some extent, we've done that also. So, in terms of background, since I was asked to say a little bit about my background, I did a PhD at Ghent University and IMEC. This is in Belgium, so this is integrated photonics, so silicon photonics, mainly, so silicon nitride and silicon. I personally focused mostly on optomechanics in those circuits at the time. After that, I went to the US for my postdoc to Stanford University, and there working more on quantum technology and also on having these different quantum systems and having them interact with each other in a way that lets you do more overall, right? So combining the strengths of different quantum systems. And then since a few years now, I'm heading a group at Chalmers where we're now nearing 10 people, and we have a completely new lab with millikelvin equipment, optical equipment, and everything you need to try to do these things at the quantum level. And of course, we're supported also by a number of grants there. And so, before I get into some examples of what we do, I'd like to describe the big picture. And so, the big picture is that I feel like we're all in this age of information processing, where computing has grown massively, communication has grown massively, and we all rely on this all the time, of course. It seems like this is not really slowing down yet. Some people say it is, but there's still really large investments, for example, in scaling up GPUs and making chips that have over 1 trillion transistors. And it still seems to be like humanity's effort is going really into semiconductor technology and software. And that might not be slowing down at all. If you look at what, for example, GPT can do, as many of you also have tried, right? With only a few tries, you can ask it to create these amazing images. For example, I asked it to make me an urn of inventions, right? And show that you can that people have taken out the transistor from this urn really first. And it does that really well. So I'm not sure that's slowing down this transistor technology. But nevertheless, I feel like if you think now of the space of all possible devices that are out there, to me it looks like it's more or less an accident of history that we're stuck with this transistor-driven world. Right? So there could have been many other devices that we might have discovered 50, 60 years ago, but we didn't. We found a transistor there, and then there happened to be a path, for example, through the transistor radio, to commercially valuable things, and then that sort of became a snowball that accelerated, right? And then we ended up where we are now. But we might have easily found something very different, and then maybe we have very different devices right now. I don't know, but I'm quite curious about that. That is what is motivating our work here. So, and then to find different kinds of devices that work very differently than a transistor, we take coherence as a starting point, right? So in transistors, the electrons behave incoherently. There's no wave effects, there's no quantum effects because there's too many collisions and everything just becomes incoherent very quickly. And so we take both wave coherence and quantum coherence as a starting point in the group. And so that's our focus, to exploit both of those. And that's, of course, shared by many groups around the world. So we want to exploit, for example, superpositions, entanglement, but also the idea that, for example, a lens can do computations, for example, doing a Fourier transform without you having necessarily to do anything for it. And so that's where our focus is, taking coherence as a starting point. And then particularly on the quantum side, our focus is on superconducting microwave and optical technology. These can be seen partly as the extensions of the things that already work very well, right? So the superconducting microwave technology is a little bit like our electronic chips with transistors, except they're coherent and they're very cold. And the optical chips, they connect to this communication infrastructure that we use every day when we use, Netflix or cloud technology or other things. And so that's where our focus is on microwaves and on optics. And so if you look at a state-of-the-art superconducting microwave quantum processor, it has on the order of 100 qubits nowadays, and it might have errors, or only like you do 1,000 operations and it makes one error. So they're pretty good already, but nowhere near close where everybody wants to be. So the question is, how do you scale up these systems? And if you look at the experiments, they're extremely complicated. Lots of cabling, it's very hard to run these things, and you have to tweak everything, and then it works maybe for a couple of days, and then you have to tweak it again. So there's lots of problems there. And it looks a lot like what classical computers were last century. So very complicated. It seems like this will be very hard to scale. Of course, it doesn't mean that this will scale, because this did, but it certainly looks like we're in a similar stage of history there with this technology. So the question is how to scale, how to reduce errors, and really how to increase the volume of space that behaves quantum mechanically. And that's what we want to help with. And so if you look at these processors, again, there's many cables. It's sort of like you're trying to control every transistor in your phone, with a separate cable. That would never work. Your phone has, you maybe use 20 buttons, but there's still a billion transistors in there. But if you were to do it like this with your phone, it would be as if you had a billion buttons on your phone. So these things really have to change in order to scale. And so when we have our processors, so that's what the superconducting microwave community is working on. But what we don't really have is storage. So how to store quantum information. There's no memory. And there's various candidates for that. So we might use, for example, mechanical systems is something we are very interested in. That could store things. Yes?
Maybe just a question. You're really saying we don't have quantum memories? Or you say that they are not good enough?
They're not good enough, yes. So, and we also don't have a way to transfer information between these different processors very well. So there's no way to connect small quantum systems, connect them together and make a larger system out of it at the moment. So, and to address these challenges, we work with these hybrid quantum systems. We try to take the best, for example, of phonons and optical photons and microwave photons, and then put it together, right? And so this brings us to this sort of challenge at the interface of physics, nanotechnology, chemistry, and so on. So you can also just see it as a fundamental science challenge. It's not just to scale up. And so, in particular, I'll focus on transfer in this talk. And so there, one of the questions is, how can you now connect microwave quantum systems? So you have several of these microwave quantum processors. What's the best way to connect them? And there are several options. You might use microwave cables, millimeter waves, but a particularly interesting one is using optical fiber, because that's how the internet already works, right? So that would be amazing if you can just leverage that. With very low losses, very low thermal occupation, and it will work at room temperature. So at this point, I'll just briefly ask if there's any questions about the big picture here, or is the big picture clear? Okay. So we're trying to then make these devices that, we want to use optical fiber to connect these things, but the processors themselves are at microwave frequencies, but the fibers are at optical frequencies. Right? So how do you convert the quantum information between these two? And that brings us to this topic of microwave optics quantum transduction. How do you take the quantum information and you move it from microwave to optical frequencies? And so here the goal is really to take a quantum state, it might be in the microwave frequency range, or it might be the optical frequency range, and then you want to move it over to the other frequencies. And so basically frequency conversion without adding noise, and without destroying the quantum state is the goal there. So the device that you're using for that, which is now a black box in this drawing, should not be measuring the state, right? Otherwise the state would be affected by that. And this device, we also know whatever is in that black box, it needs to use some sort of frequency conversion, or at least 3-wave mixing, could be 4-wave, 5-wave mixing, or higher order processes as well. And the reason is that for that is that the microwave frequencies, of course, have much lower energies than the optical modes. And so for that, you need at least one pump. So you need an optical pump. And that is actually the key source of that these things are not yet working extremely well. It's because you need a pump that leads to problems which I will discuss. So I'll skip this. So then the question is, what will you put in that black box? And there's many options, but the one that we are focused on is using acousto-optical systems. That's mainly for reasons of minimizing the energy that you lose in this black box. So that because of this optical pump, we believe that acousto-optics is looking like one of the more promising ways to move forward because it minimizes this energy that we're losing. So that brings us to this question of you want to convert frequencies with mechanics, and so what is the quantum limit of an acousto-optic modulator? And that's really what we're working on. So you might picture a device that looks like this. So you could have an optical cavity with one of the mirrors is moving, so it's not a mechanical system, but then it also connects to a superconducting circuit, which could happen, for example, through a piezoelectric material. And as I said, so you need an optical pump. So in the optical cavity, there's an optical pump, and some of the pump light that's resonating in this cavity is being scattered and is also being absorbed. And the absorption there is the key problem, because whenever you lose an optical pump photon, the mirror, there's some energy that's dissipated, and now this mechanical mode heats up a little bit. And then when the mechanical mode heats up, then the quantum conversion process no longer works, because you now get noise in the system. So, and this is especially bad in the devices we want to be using, in these integrated devices, where most of the established ways of working with these systems, they work with suspended structures because they want to confine this mechanical mode. They want to prevent the mechanical mode from leaking away. Right, so you have some sort of suspended structure, like shown here, and then there you have an optomechanical interaction. But then when there's some light being absorbed there, there's some heat being generated, and that heat cannot go anywhere. It's basically trapped there. So now the conversion process doesn't work for a very long time. Okay, I'll just skip that. So this heating problem is really the key problem. So if you look at what devices have been doing so far, so if you look at this is the year of the publication, and then you have the efficiency of the transducers, the efficiencies are really going up very fast, sort of an order of magnitude per year. So if that keeps going, we'll be at 100% efficiency very soon. But the problem is that the efficiencies go up, but also the noise is not improving. It's actually also going up if you increase the pump power, for example. So that's the key challenge. How do you get rid of this noise that's being? And
question.
Yes, question.
What do you mean with the trade-off?
Yeah, so I mean there that
the separate programs.
Yeah, so so in this transducer you have it's a 3-wave mixing process, right? So you have a pump. And if you increase the pump power, you can increase the efficiency. But you also increase the absorption then, and then you also increase the noise. So that's where the trade-off comes in. Yeah. So you have to choose: do I want high efficiency or high noise? And it seems like at the moment there's nobody who can do both. Like you either have to have high efficiency or a low noise. I might have misspoken. So you want low noise and you want high efficiency, right? But nobody has them at the same time at the moment. Yeah, and so that is the key problem here, is that this is absorption in the optomechanical section of whatever device you're working with. This is just a schematic here. It doesn't matter what it looks like. There will always be some absorption from this one. Okay, just a quick Q&A. So any more questions about this problem that I've described?
Do you think there is a fundamental trade? Because what you just discussed, it's not a fundamental trade-off, right?
Yeah,
Do
I
you
feel
think
that
there is a fundamental trade-off?
No, I don't think it's fundamental. No, but I think it's very hard, and that's what we're working on, is to try to get around this. So I don't feel it is fundamental, or we wouldn't be working on it, but it's a very hard problem. Yes.
So as far as there are no like at least theoretical bounds, I don't know, some kind of black body or...
No, I think because you could in principle have a material, with absorption that doesn't matter at any of the scales that we're talking about. So. Yes?
Is this working at a quantum level, for example, single photon or single photon, or is it like classical regime?
The goal is to do it, with quanta, right? But it's very, very difficult at the moment. There's only a few experiments, and then they have to work at very low efficiencies in heralding schemes, so only not in deterministic schemes. So because of this problem. Okay, and so this brings me to one of the efforts we have in our group now, one of the things we started with, which was really like, so there's this problem, like basically all the research groups are dealing with this problem in one way or another, but it seems like at the time at least nobody was really trying to get around this trade-off more fundamentally. So we went back to this problem of heat. So you have heat in the device and you want to get rid of the heat. So what's the best way to get rid of the heat? Well, you attach it with other materials around the device, right? But then you create a problem for yourself, because if you do that, then you still want to confine certain things in that structure as well. You want to confine the mechanical mode you care about, and then you want to let the heat leak away. So it's like you want to confine certain phonons, but you don't want to confine other phonons, right? So how can you let heat phonons escape while having coherent phonons stay there? So that was really the problem that we started with. And the solution that we've been exploring is that you can use coherent phonons that have large wave vectors, so that they don't actually manage to couple to anything in the substrate. So it's basically like you would confine optical waves, right? But for phonons. And then the challenge becomes now, how can you have these sorts of phonons actually interact strongly with optics still? Right, so now we have a structure that's not suspended, it's completely clamped, right? So it's attached all along the structure. So this is one of these cavities, it's an optomechanical crystal structure. So you have a defect region with mirrors, but this is all attached to a substrate. And so, hopefully, and that's what we're seeing, at least at the moment, the heat will really dissipate much faster. But can you then still get the same performance, as a suspended structure? And that's, has been unclear when we got started, at least. How am I on time, by the way?
It is 1:35. Sorry.
Okay,
so we have some time.
So 10,
yeah.
15. Okay.
Yeah. Perfect. Yeah.
Okay. So as I said, the solution we came up with is to use mechanical modes with very large wave vector, but then you have to have the optical mode actually. There's a three-wave mixing process, so you have two optical waves, and these optical waves then interact with each other in a counter-propagating way. So they interact with each other such that the momentum is conserved in this process. Right? And so that's not a process that we're then exploiting in these structures. I'll be a little bit quick here. So, and then that was sort of the theoretical concept, but then you have to actually find a device and a set of modes that actually do interact strongly. And then between the previous slide and this slide was about a year of effort, looking for what kind of devices could actually make this happen. So, and then the device that we found looks like this. So it's not a mechanical crystal. It has an optical mode that looks like this, a mechanical mode that looks like this, and the mechanical mode has a wavelength that's half of the optical mode's wavelength, in order for this phase matching or momentum conservation to actually happen. And then, so I hope, are there any questions about this? How this works, this three-wave mixing, and then the fact that it's on a substrate. And then so that we made these devices, we measure them at room temperature, and we see the things that people typically like to see on the mechanics. So magnetically induced transparency, amplification, cooling, and I'll be quick on that. But then the interactions actually were almost as strong as you would hope for in a suspended structure of this type. So the interaction rate was almost a megahertz there. So that gave us some hope that this could really actually work. And then now we're doing measurements at cryogenic temperatures, and for example at 4 Kelvin we do see that it looks like you can put a lot more power in at least before the optical resonance starts shifting. So that's already a hopeful sign, but we actually have to look at the quantum noise in the system, and that we're still working on.
So why is the blue shift there? Why does it increase the frequency?
You mean here?
Yeah.
Yeah, it's a good question. We're thinking it might be free carriers, but we're not completely sure yet. And then we also want to use these optomechanical structures that we've now developed to actually make an entire converter between microwave frequencies and optical frequencies. And so we have designs for that. So you can see here we have designed electromechanical crystals that couple to these optomechanical crystals. And so, and these designs actually do look at least design-wise or like simulation-wise that they could perform well. And so this is what the whole transducer then looks like. So optical node and mechanical node here, and then this is where the microwave field impinges on electrodes there. Okay, then I'll take a brief moment to come back to the big picture. So now we started from how can you connect these microwave quantum systems to each other and make a larger quantum system from smaller ones. But another way of thinking about these devices is that there are, I'll be a little bit quick on this, so there are lots of people who also want to make purely optical quantum processors, right? And one of the things they really want is a source for entanglement, right? And microwave circuits are actually very good at creating entanglement deterministically and very fast. So if you have one of these transducers, you could also be using the superconducting circuit as a source for entanglement for the optical circuit. Right, but then the question is, how do you do that with an imperfect transducer between these superconducting and these optical circuits? And now I'm going a little bit quick, so just big picture. So how do you add nonlinearity to the optical circuit using a bad transducer, as those devices currently are, and the superconducting circuit? I'll skip over this, and the scheme that so we came up with a scheme to do this, and so it turns out you can actually herald optical entanglement from a microwave circuit using one of these transducers. And so I won't go into the details there, but it then looks like you can create these optical cluster states from a microwave circuit and a bad transducer. Okay, I just also want to mention that these transducers could be interesting for other things than what I've talked about so far. So they could be used for optical readout and control of microwave qubits without doing quantum conversion. They could basically be used in any situation where you want microwaves to control light also. So it's sort of like a much broader need than what I've mentioned so far. And especially when there are power restrictions also. So our lab, and also in my previous work, we've also done a bunch of related things that are not really about microwave optics conversion. For example, we're looking at these mechanical systems as memories, as I mentioned, so for quantum RAM memory basically, because the mechanics could actually store things potentially for a very long time. So there are some measurements in Caltech where they can have a T1 time of a second. And we've also been working on lithium niobate circuits where we made some of the first on-chip lasers on lithium niobate, and so non-reciprocity also. Just mentioning that we work on these things, but then you can find publication if you want to. And with this, I just mentioned that I've focused so far mainly on that optics. The optics has can give you large range. It's very good at that. That's why people use it in networks. Right, and superconducting microwaves are great at giving you deterministic operations, so quantum nonlinearity. But there's really like a much longer story with various advantages and disadvantages of these different systems that can be combined in different applications that I won't get into now. So there's a much larger question: is like, what's the best way to combine the strengths of different quantum systems? And so that's a big question. Right, and then just want to acknowledge our funders and the group as well again, and also also my family, because it's important to keep your priorities straight. There's more to research, to life than research, and then leave you with this idea that I would hope at least that the inventors of the transistor would look at this kind of work, with an approving nod. We don't know where it's going to lead, but I personally believe it's worth pursuing, even if transistors keep going as they are with AI, etc. So I think it's interesting work. So thanks for your attention. If you have any questions. Yes.
Simple question. Why are mechanical systems better than other devices for memories, quantum memories?
I would say it's not known if they are better
Okay.
at the moment, yes, but they could be very interesting because first they can work at the same frequencies as the superconducting microwave circuit, so 5 gigahertz for example. They can be super compact because the speed of sound is it's like 5 orders of magnitude different from the speed of light, which means that every device can be like many orders of 15 orders of magnitude smaller in volume in principle. So that you can use band gap methods to prevent any crosstalk, so there's no crosstalk. But there's still a lot of questions also. So people have not seen these long T1 times with electrical readout. They've only seen it with optical readout of the mechanics so far. So there's still some questions.
Okay.
Yes.
So can you say something about the conversion efficiency and added noise of your device compared to state of the art?
Yeah, so for the release-free devices, you mean the ones that are
Yes.
planned? We don't know yet because we're still building them and measuring them. So we don't know yet, but we hope it could be quite a bit better. Yeah. So in the measurement I showed is preliminary data, the power that we could put in before we see thermoptic shift. There it looked like it was about 80 dB more at minimum. But that's very early data, so I don't dare to say too much yet. So. Yes?
I wanted to know, like this release-free approach, how it compares to these two-dimensional optomechanical crystals. Is it like an order of magnitude faster thermalization?
Yes. That's a very good question, and so we don't know yet. That depends on this data that we're still taking. But sort of, if you want a guess, then my guess is that it will be better because the contact area is sort of larger. And there's also some other advantages that we are thinking about that could be advantages, which is that in these 2D structures, you use a different method of confinement, and you need to have like full in-plane band gaps to prevent leakage sideways, while we use a more robust sort of traditional way of confining things, which is internal reflection, right? And so it could be less sensitive to disorder also, which is matters a lot if you try to make these devices in the lab. And so even if it's sort of on par performance-wise, which I think it might be better, we don't know yet, but it could be interesting just because it works more easily.
Yeah. Another way to avoid this heating is to increase the optomechanical interaction. Do you think your system already achieved maximum coupling you can achieve?
And that's also a very good question. I don't think we've achieved the maximum because it was just sort of the first design that we came up with, and it had half a megahertz.
Can you improve the coupling one of the magnitude of 2?
Yes. Yeah, we know that, for example. Yes.
Material or structure.
Sorry, can you repeat the last
By
part?
changing the material or structure, how you can
Yes.
how do you improve that?
Yeah, so just even staying with the same material, silicon, and the same sort of claddings, etc. I think we can get a factor of at least 2, probably. But I mean, that's just a guess because we don't have that. But because in the defect unit cell, we know that the interactions are stronger than in the full mechanical crystal. So there's some overlap that we can improve, and we just haven't had time to try that. So.
And then if you were to go to different materials and structure, like what could it be?
Yeah, I mean, in principle, like these optomechanical coupling rates, they can scale fast if you with increasing refractive index. So going to higher refractive indices could be interesting. Of course, there's always a trade-off because silicon is a very nice material to work with if you want to pattern complicated things. So I'm not super tempted to try something else at the moment, but in a couple of years, maybe that could be interesting.
Any other question? Okay, if not, thank you very much.
Thank you.